In this lecture, we will be looking at examples of the limit comparison test for the convergence of infinite series. Let's recall what the limit comparison test says. We have two series, the sum of ANs and the sum of BNs, both of which are sums of non-negative terms. And we have that the limit as n goes to infinity of the ratio of the terms, AN over BN, is some positive constant C. Then the result of this is that both series either converge together or both diverge together. They have the same type of behavior. And the reason for this is that this limit condition means that for large n, we have AN over BN is approximately equal to C, or AN is approximately C times BN for large n. And that means, as we go further and further down the line for our sum of ANs, the terms look more and more like a constant times the terms in the BN sum. And this tethers them together in terms of their behavior. So let's look at an example. And with the knowledge that we have prior to learning the limit comparison test, we might try the direct comparison test. So consider the sum, n going from 2 to infinity, of 1 over root n cubed minus 2. So the first thing we might note is that for large n, that expression, 1 over root n cubed minus 2, is going to be close to 1 over root n cubed. The dominant term in the denominator is the n cubed. The 2 is becoming more and more insignificant as that n gets large. And we have n cubed minus 2 under the square root sign. So this thing, the larger n gets, it looks more and more like 1 over root n cubed, or 1 over n to the 3 halves. And so maybe we can set up a direct comparison with the sum n goes from 2 to infinity of 1 over n to the 3 halves, which we know is a convergent p-series, because the power of n in the denominator here is 3 over 2, which is bigger than 1. Remember, for a p-series to converge, that's the criteria, that the power of n in the denominator. And maybe we should recall that a p-series we write as one sum from n equals 1 to infinity of 1 over n to the p. So could we set up for a direct comparison test with this convergent p-series? Well, let's try that. We would say, let's build the necessary inequality. N cubed minus 2 is smaller than n cubed. Square root of n cubed minus 2 is thus less than the square root of n cubed. And then, of course, cross multiplication tells us that 1 over root n cubed is less than 1 over root n cubed minus 2. So this represents the term from our series, and the 1 over root n cubed, which is of course 1 over n to the 3 halves, represents the term from this convergent p-series. But here's the problem. We now have a term that is smaller than the terms from our given series. So it is the case that the sum n goes from 2 to infinity of 1 over n to the 3 halves is smaller than our given sum. And that means the direct comparison test does not help us, because this smaller sum is convergent. And to say something about this series, to try and claim that it is a convergent series, which we expect it to be because of this argument we made here, we need to find a larger convergent series that dominates it. Finding a smaller convergent series doesn't help us, so we cannot conclude anything. From this attempt at the direct comparison test. But that being said, we really do have the right idea here. The idea that this sum, as n is getting larger and larger, is looking more and more like the sum of 1 over n to the 3 halves, and thus our sum should converge, that's still a valid intuition. Our direct comparison test, it's actually worth noting, would have worked just fine if this minus 2 was a plus 2. But what does this mean? We still intuitively know this thing is going to converge because of our argument here, but we can't use a direct comparison for it. We can use the limit comparison, and that's the sense in which the limit comparison is a bit more robust than a direct comparison. And this is how we use the limit comparison test. Given your sum of the a sub n's, find a simpler sum of b sub n's that we understand. So by understand, we mean we know it either converges or diverges. Then do the work to establish the limit condition. So you take the ratio of the terms from each series, take the limit as n goes to infinity, and get a positive constant, and then apply the limit comparison test. And a very common choice is to go through the exercise we just did, where you're given this sum of the a sub n's and you want to choose your other series, or the b sub n's will be the expression that a sub n behaves like for large n. For example, what we just saw in example 1, when an is a fraction, when your given series is a sum of some fraction, choose the bn's as the ratio of the dominant terms. And what that will do will allow things, the non-dominant terms, wash out in this limit, and then you can use your simpler series to make your conclusion about your given series because they both converge together or they both diverge together. So to come back to example 1, we noted that this sum n for n large was about 1 over root n cubed, and that approximation gets better and better as n goes to infinity. So we'll now use that as comparison. And to set up for the limit comparison test, we will say that these terms in our given sum are our an's, and these terms will be our bn. For the limit comparison test, we look at the limit as n goes to infinity of a sub n over b sub n and simplify. So we have the limit as n goes to infinity of our a sub n's are 1 over root n cubed minus 2, and our b sub n's 1 over root n cubed. And now we need to simplify. So this is the limit as n goes to infinity. We have the 1 over root n cubed minus 2, and then dividing by 1 over root n cubed is the same as multiplying by root n cubed. And now we just compute our limit, and we note that this is the same thing as writing the limit of the square root of n cubed over n cubed minus 2. And then we know with our limit laws, because the square root of x is a continuous function, we can bring the limit inside the square root sign. So square root of the limit as n goes to infinity of n cubed over n cubed minus 2. To evaluate the limit of a rational function like this, identify the dominant term in the denominator, and divide every term in denominator and numerator by that dominant term. The dominant term in the denominator being n cubed. So we have n cubed over n cubed in the numerator, divided by n cubed over n cubed minus 2 over n cubed in the denominator. So this gives us the limit as n goes to infinity of 1 over 1 minus 2 over n cubed. And then applying our limit laws, we know that this 2 over n cubed goes to 0. And so this becomes the square root of 1 over 1 minus 0, or the square root of 1, or 1. And of course 1 is greater than 0, and so we have established the condition that we need to conclude that our given series will converge by limit comparison test. So to recoup what we've done, we've established that the limit as n goes to infinity of the ratio of our terms from our series is 1. The new series we worked with is a convergent p-series, and these two things together for the limit comparison test ensure that our given series also must converge. So this is a very common way to use the limit comparison test. We look at another example, and we'll take a similar approach here. So for this sum, this is a rational function. Let's identify the dominant term in the numerator and the dominant term in the denominator and choose our Bn to be the ratio of those dominant terms. So first we note in the numerator the dominant term is 5n cubed. And in the denominator, really to get the dominant term, we would have to multiply this out. We would have to FOIL out the bottom, and we see the dominant term would be n squared times n squared, or n to the 5th. So this sum, as the terms get larger and larger, the terms will look more and more like 5n cubed over n to the 5th, or 5 over n squared. And that choice of Bn will give us what we want when we take the limit of the ratio of our given terms to this 5 over n squared term. And we note that the sum, n going from 3 to infinity, of 5 over n squared is also convergent. So this is a convergent p-series. And again, p is 2, which is bigger than 1. Hence, the series converging. So we found this simpler series that we know converges. And if we can now just establish that the limit of the ratio of our given terms to these terms is something non-negative, some non-negative constant, then we can conclude that this also converges. And again, we already have an idea that it should, because if this sum really does look like the sum of 5 over n squared for large n, it should converge. And it in fact does. So let's show that. So if we call these terms our a sub n's, for the limit comparison test, we need the limit as n goes to infinity of a sub n over b sub n, which we know is the limit as n goes to infinity. Our a sub n's, we have 5n cubed minus 3n divided by n squared times quantity n minus 2 times the quantity n squared plus 5. And we're dividing by the bn's, which is 5 over n squared. And now we need to simplify this limit. So first we note that dividing all of this by 5 over n squared is the same as multiplying it by n squared over 5. So we have 5n cubed minus 3n over n squared times n minus 2 times n squared plus 5. All of this multiplied n squared over 5. And we get an n squared term in the top and the bottom pairing up to cancel. So to compute this limit, we need to multiply out the denominator. So the numerator, we have 5n cubed minus 3n. In the denominator, we have a 5, and then we FOIL this out. So for the first terms, we get an n cubed. For the outer terms, we get 5n. For the inner terms, we have a minus 2n squared. And for the last terms, we have a negative 10. We can factor out that 5 in the denominator to make things a little nicer. And recall the way we do this is to identify the dominant term in the denominator and divide every term in the denominator and the numerator by said dominant term. And we see that the dominant term is this n cubed. So we divide every term by n cubed. So we have 5n cubed over n cubed minus 3n over n cubed in the numerator, divided by n cubed over n cubed plus 5n over n cubed minus 2n squared over n cubed minus 10 over n cubed in the denominator. We simplify. 1/5 times the limit as n goes to infinity. In the numerator here we have a 5 minus 3 over n squared. And in the denominator, n cubed over n cubed gives us a 1. We have plus 5 over n squared minus 2 over n minus 10 over n cubed. And then a direct application of the limit laws. The limit of the quotient is the quotient of the limits. And then the sum of the limits is the limit of the sum. This results in each one of these terms with an n term in the denominator going to 0. And this whole thing becomes 1/5 times this limit of 5, or 1. And this means we have now established the condition that we need for the the limit comparison test. So we have the ratio of the terms, an over bn, as n goes to infinity, being 1. And we know our simpler series is a convergent p-series. Therefore, our given series also converges by the limit comparison test. So these are two classical ways of using the limit comparison test. And again, it isn't always the case that you use it in this manner, but this is a very common way to use it. You can identify, based on dominant terms, a simpler series to use and apply direct comparison.